Hello. Thank you for making it out to the very last talk of the day. Has anyone not had dinner? Okay, do you guys want to go? We'll wait. So today, Rogan and I are going to be talking about some work we did on a piece of hardware, an end-to-end implementation of a covert USB implant, which is the trendy thing we're supposed to call it after the NSA leaks, that provides sort of remote access through physical USB ports without needing to use the network on the device. So if that interests you, then hang around. So the quick intro, we're from a company called SensePost. We've got an office in South Africa and in London. We're a penetration testing company. It's what we do, a couple of other things. It was founded nearly 17 years ago in Roelof's bedroom in Pretoria. One of the guys who was around at that time is hanging around at the back there, Haroon. And Rogan is the primary researcher for this work. So if you get really upset with him, then please mail him. But if you have nice things to say, then mail me. I'm Dominic. Okay, so the reason we pursued this particular attack was that we think it's important to have a threat model which represents some kind of reality. And I think a lot of the time we're walking around worried about pianos falling on our head instead of walking around worried about being mugged. And I think part of that is people like us stand up and present attacks that people watch at conferences, and it gets some press, and then people run around trying to defend against those. And then you get vendors trying to convince you that like next generation firewalling requires some focus. And so what we wanted to do was make sure that we were building attacks which represented things that people were actually getting attacked by. And so what we did is we went to go and look at what attackers were doing. So we looked at some attackers, and the Snowden docs that were dropped had that ANT catalog and the Teo stuff, and in the sea of all the offensive techniques in there, there was this catalog of hardware-based implants. And this one in particular was quite interesting. Well, the cotton-mouth devices, they were miniaturized USB implants that would give you remote access to a machine over their custom RF protocol. So the real bad guys, depending on what your threat model looks like, we're doing that. On the other side of that scale, if you imagine a scale from apex predator down, we were involved with some real criminals in some attacks that were happening against institutions, some of our customers. And what they were doing is stuff that was quite lame, but worked really well. So they would pay people to put hardware keyloggers on machines for people who had credentials that would be useful, so we can get that person's credentials because they can make a transaction, and that person's credentials because they can approve a transaction. And then they would pay either the same person or a different person to then go make an image of that machine. And they would go buy commodity hardware. And to give you an idea about their sophistication, they'd even try and match the color of the hardware to make sure that they had the same computer. And they would restore the image on that. And then they'd pay somebody else to put this little 3G to Ethernet bridge on the local network. And so that they've got creds, they've got the software, they're on the local network. And this worked ridiculously well. They took numerous organizations for multi-million rands, so about £2. But you can live off of £2 in South Africa for a couple of years, and maybe a Porsche. And so if you've got the apex predators attacking through hardware, and you've got the kind of the bottom feeders attacking through hardware, we sort of hypothesized there must be a range of potential actors in the middle. I think that's unproven, but there's at least two attackers doing that. And the theme that they seem to be using was this hardware bypass of software security. So where we would normally quote the 10 immutable laws that Haroon put up this morning, physical attacks are lame, we've got to own them through SQLi or through phishing attacks. Here you've got real bad guys owning people quite successfully through hardware. And so we thought, well, this is an indicator of real attacks that seem to be problematic because the defenses in the space are really, really bad. So if you take hardware keyloggers as an example, these are a persistent problem, and the best defense we have against them is physical inspection. Now, physically inspecting all your USB ports across an entire organization, I think we can at least acknowledge up front as a shit defense. Even if we don't want to acknowledge that maybe trying to do the same with patches is equally bad. And if you think about the way people defend against USB-borne attacks, it's either a worry that they'll drop malware through mass storage, or it's going to be some kind of unauthorized networking device, be it a modem or tethering through a phone or a wireless card. And the defenses we rely on are placed elsewhere in the stack. So maybe the closest we can get to it would be something like antivirus, in the hopes that that would block the USB malware. But we've got things like the FireEye sitting on our network trying to detect the C2 beaconing, and we've got proxies trying to prevent unauthorized access out. The defenses for these things are placed elsewhere in the stack. But what we saw with these attacks, everything from the sophisticated, I mean, NSA was doing that stuff in 2008, through to these other criminals, is they were bypassing all of that stuff and doing it quite successfully. And so we set about building something that we thought we could use to demonstrate this kind of risk in an engagement, and hopefully drive some changes at our customers, knowing that this is probably something that criminals might actually use them against their network. So we had a couple of objectives in what we were putting together. The first is we wanted something that was complete, that you could actually use in an attack from beginning to end. There's been some prior work in this area where they've built parts of it, and we wanted to kind of put the whole thing end to end. We wanted it to be remotely triggerable at a time of our choosing. So we didn't want it to be a fire and forget, or if you've got one bite at it and if it doesn't work, you're screwed. We wanted to be able to dynamically try different things at different times that we thought were appropriate. We also wanted to avoid obvious vectors, so we didn't want to drop a Metasploit payload over mass storage. We wanted to try and be a bit more sneaky about it. So I think that'll drive better defenses. You don't get a pass just because it happens to trigger one of the other defenses. We wanted it to be automated from beginning to end. We didn't want it to be high user interaction. We wanted to run it and hopefully get a shell. We wanted to not use the network of the device. So we wanted to move that into our own hardware. On the one hand, that avoids network complexities. Any of the penetration testers in the room will know sometimes you get those funny proxy setups where you can't tunnel your stuff out particularly easily, and you've got to spend time building alternative exfil methods. But the other hand, it makes it easier to bypass detections looking for us trying to get that data out. And then lastly, related to that, we wanted it to be designed in a way that would be difficult to forensically detect. So that's different from building some malware and then fudding it to prevent AV from detecting it. Can we do it in a way that prevents it from doing things that would typically get detected? So talked about some of that, like avoiding obvious malware vectors and avoiding the network. But since we're using hardware, we had an advantage to move a bunch of stuff onto the hardware instead of putting it on software running on the host machine, for example. We could make sure things run in memory. We could make sure we were using innocuous-looking devices that didn't necessarily trigger on rules that might make this look malicious. So those are our design principles.
So we've been building on prior work that's been done in this field already. Adrian Crenshaw's Plug and Pray, the original USB malicious device. The Hack5 rubber ducky, I think everybody's familiar with. Basically, the triggered or scripted keystroke injection. What we've done takes this a step further, which we'll show you in due course. Michael Osman and Dominic built the Turnip School implementation for the NSA playset, which is basically it was a proof of concept to show that they could design the hardware to be small enough to fit inside a USB-A connector. And they did that. They never actually took it any further, to demonstrate the actual Wi-Fi or the wireless capabilities. Apparently the chip that they chose was a pain to work with. And there's a bunch of other more recent things as well. So this all came about when I discovered a tiny little dev board called the Cactus Micro Revision 2 from a company in China called April Brother. It is a combination of an aTmega 32U4, which is maybe familiar from the Arduino Leonardos and thereabouts as an Arduino type chip. But it also combines an ESP8266 chip, which is a Wi-Fi capable microcontroller. So we've got two parts there. You'll see that there's actually a little carrier board. Well, there's the underlying board, and then there's a module that's soldered on top of that. The bit that's soldered on top is the Wi-Fi capability. So those two microcontrollers can talk to each other. So that gives us something that's small enough in a physical form factor to be legitimately a flash drive size thing. Great big Arduino boards that everybody's familiar with. It solves the capability gap where you've got your aTmega chip not having any Wi-Fi or communications capability, and of course the ESP8266 chip not having USB capability, not having any kind of ability to interface at a USB level. And a great part of it is that it was ridiculously cheap. They're selling them on Tindy for about $12 shipped from China, free shipping. You don't have to pay $25 for rush shipping. So this was great. It did have some disadvantages, most notably the fact that it used a micro USB connector, so if you wanted to plug it in, it would be hanging off a cable. So when we decided to go further with this, we wanted to build our own board. So we designed it with a USB-A connector, obviously, to solve that first problem. We added a micro SD socket for storage, and we connected a couple of the extra pins. The I2C bus on the original dev board was not connected. You had to solder some jumpers and resistors on, so we connected that. We designed the board so that it would fit into an off-the-shelf casing, and we used a Hall effect sensor, which you can trigger with a magnet, so that once it's in the case, you don't have to disconnect it to reprogram firmware onto the AVR. So a couple of nice enhancements to the original board. We pretty much use the same schematic, so it's mostly compatible. So for those at the back, this is what it looks like. It's totally believable as a flash drive. This is our finished hardware. And yeah, it's pretty neat.
Rogan always forgets the split, so I have to.
Yeah, got to remind you. So it has been released as open hardware. You can get the schematics, the bill of materials, the Gerbers, etc., from our GitHub repo. We are looking to partner with somebody to get it released as, to make them available cheaply and inexpensively, so you don't have to get them made up yourself. So this is our basic sort of attack scenario. We've got our attacker up on the left-hand side, and our target down on the bottom right-hand side. The attacker is connected to the ESP8266 over their own Wi-Fi infrastructure, so they'd set up their own access point. The ESP8266 is running a variation on the ESP Link firmware, which is a very simple Wi-Fi to UART bridge, which we've modified fairly heavily. The ESP8266 is communicating with the 32U4 over a UART, a serial link. The 32U4 is using the Lufa stack, which is a really great USB framework for developing USB class devices. And then that obviously is talking to our target over the USB interface. So that's sort of conceptually how it works. Obviously, the ESP8266 and the 32U4 are in one single unit. So the first part of the capability is to get back to the the keystroke injection that the rubber ducky and the USB plug-and-play device pioneered. So when I first built it, I started off by connecting to it using like Netcat and typing in byte 4, which means spit out an A on the other side over the USB connection, and type 0 to lift the key up again. And that's obviously very inconvenient. Quickly iterated to write a program on the PC, on the attacker's PC, that would let you press a key and it would do the translation for you. And then monitor your mouse movements and emit those as well. It was a really terrible program. It was written in Java, which the first person will tell you this was the wrong choice of a language to write something that's monitoring keystrokes and mouse movements. It has lots of horrible corner cases, like you press Alt-Tab and you switch away from your program. You can't send Control-Alt-Delete and those sorts of things. So with a bit of thought, I then realized that, well, actually, we've got this is a solved problem. There exists a protocol for sending keystrokes and mouse movements over a network, and it's called VNC. So what I did then was I modified the ESP link firmware and implemented a VNC server on the ESP itself. And that's great. You can now use any of a myriad number of VNC clients, mature, well-debugged, et cetera, and all I needed to worry about was a relatively small amount of code on the ESP. And of course, there are also command line VNC clients which allow you to script your actions and trigger those when you want to. The Loofah stack is really great because it provides a number of implementations of different USB devices that you can then build upon. Different USB class devices. And the great thing about USB classes and the class drivers that go along with them is that they're standardized. And so the various operating systems all come built in with drivers for these standard USB classes. Which means that if you plug in a printer, you don't necessarily have to have a driver in order to speak to it. You may need to have a driver that speaks the language that the printer understands, but you can interact with the printer itself. You don't need a driver to plug in a sound card, a USB sound card or a USB headset or something along those lines, because the drivers are built into the operating system. And this is great from a usability perspective. You no longer have to worry about CDs with driver software on them, especially in these days where you don't actually have any optical drives anymore. But it's great from an attacker's perspective as well, because you can plug something in and it will just work. You don't need to try and convince the user to install a custom driver that will interface with your device. And in fact, in many cases, you don't need any special privileges in order to install these drivers. You just plug it in and the operating system does it for you. So far what we've done is we've managed to replicate the rubber ducky functionality with an extra twist in that we can trigger it remotely over Wi-Fi when we want to, rather than hard coding the delay before the payload triggers. Those sorts of things are problematic when you run into a case where it's plugged into a locked workstation. You don't know how long it's going to take before it's unlocked and your script should execute. So what we've then added on top of that is the ability to have a back channel, a bidirectional binary clean pipe that you can communicate with from the attacker's side over Wi-Fi through to the target side over USB. You've got a completely 8-bit clean channel that you can transfer arbitrary data in both directions. And that is certainly the novel part of this device. So the way it works initially is that you have your scripted VNC first stage, or stage 0. That's typed in, so we try to minimize that as far as possible. It's limited by the speed that your operating system will sample the keyboard. We're basically getting around 90 characters per second, which is pretty slow. So we tried to make that as small as possible. The next stage is then transferred over the HID interface, over that binary pipe that we managed to establish, and that can be larger and more complex because our HID interface is substantially faster.
So there was a requirement in us to be quite sneaky. Because you're interfacing with a user's machine, and you don't want to be popping up windows and having text fly around. So you've got to think about how you're doing it. So the first thing we did was, well, not the first thing we did, but one of the ideas that came to us is it turned out that there was a guy speaking the same time as us at DEF CON about something called a mouse jiggler. We were like, what is a mouse jiggler? So we went to Google mouse jigglers, and it was Phil Polstra, who's spoken here before. And it turns out a mouse jiggler is a little thing which jiggles the mouse to prevent the screensaver from activating. So we thought, oh, that's actually pretty neat. That's useful for us. So what we've done is we built in a mouse jiggler, and it just moves the mouse 1 pixel to the right and then 1 pixel to the left very slowly, and effectively prevents the screensaver from activating. The other cool finding from that is that the operating system seems to smooth that, so you don't actually see the mouse moving at all. It doesn't look like it's moving, so it's not visible. The next thing was, our first instinct was to try and minimize the payload that's typed as much as possible. And you can see that my efforts at doing that, there's a horrible bash script that tries to minify Python. The problem with that, we could get it really tiny, but there's still a black window popping up with text being typed out, funny characters. It's the kind of stuff that's going to make people call an exorcist. So Rogan then came up with some really good ideas. It made our payload a bit bigger, and some things we do is we will change the text to be the same color as the background. So after about 4 seconds, the text disappears. There's just a black window. The next thing it does is it moves the window off the screen. Now, it doesn't minimize it because you still need that window to have focus so that the keyboard input is going into it. But it's effectively moved off screen, so you can't see it. And then, as Rogan was pointing out, we then bring up this generic HID pipe, which allows us to transfer data without this clunky typing thing. And at that point, we can background that process. It doesn't need to have focus. You can go fully into the background. And those were some of the things we did that made it a little sneakier and why we think it can work quite well. Oh, and sorry, actually the last bit of that is, so we chose to use a generic HID device. It's an innocuous looking device. It's not a network card. It's not something that might look strange to a forensics team or an incident response team or a threat intel team. But it could be other things. Rogan mentioned the idea of it being a printer, for example, or an audio device. Anything which can send data back and forth, you can potentially use. There's some overhead in developing a protocol that's going to work over that, but it's not impossible.
So one thing I realized in building this is that working in a development environment is not nearly, in an embedded development environment, is not nearly as comfortable as working on a PC, for a number of different reasons. The one is that debug logs are not a thing. So any debugging that you do, especially on the ESP8266, if you manage to trigger any kind of errors, it jumps out of bounds, you take too long to process something, the ESP8266 reboots, and you lose everything that you've managed to log. So that's a pain. But then just silly things that you take for granted on with an existing operating system, like flow control, like telling the TCP sender to stop, I need time to process this sort of thing. It actually becomes a really difficult problem to deal with in multiple places throughout the stack. We take for granted a lot of things that are readily available in your desktop environment. So what I ended up doing in order to have some kind of insight into what was going on in this dev board was I ended up writing my debug logs over the UART between the two microprocessors, and I snooped on the UART using additional USB UART adapters, which they're just basically eavesdropping. And those were then reporting into a screen on my PC. An old scrap of Python that reads the input from multiple USB interfaces and just interleaves them on the terminal, so you can actually figure out what the heck's going on. And what ended up happening was that in our new dev board, in our new hardware that we built, they didn't have enough space for the test pin headers down each side. So we obviously made sure that we had test pads to probe the various signals. But what it meant was, just because they're pins, you can't actually, I mean, they're just a flat pad, you can't actually clip a test clip onto them. So we had to use pogo pins, which are these spring-mounted pins that press up against the test pads of the device. So I designed and laser cut a test jig that would hold the board in place while these pins are pressed up against it, so I didn't have to like press these things and press enter with my elbow kind of story while I'm trying to watch what's going on. So actually the board that you see on the side there is a USB serial interface. That's not the test hardware at all, that's just a teensy LC. The actual hardware itself is sandwiched inside that white 3-layer structure or 4-layer structure with the pogo pins pressing up against it. And for those of you who've been to DEF CON, this was something that we were busy with in our hotel room in the Flamingo. That's the pink chairs that you can see in the background.
And Rogan did like an interpretive dance as he was debugging this. So what you'd see is he'd run it, and he'd get really excited, and he'd stand up in his chair, and he sort of did a little dance. And then the thing would just turn off, because that's what happens when it goes wrong. And you'd see him sort of walk dejectedly back to his bed, sulk on his bed, and then get up and try again. So I tried to get a video of this, but every time I tried to get a video, he spotted me. So yeah, things to do 4 in the morning in the Flamingo. Okay, so we're going to give you some demos. So we're from Africa, and as Africans do, we travel with chickens, but the UK would have none of this, so we were not allowed to bring any of our sacrificial animals to sacrifice to the demo gods, and instead we've decided to give you videos, which is our excuse, but we promise they're real. You can try them yourself. And the first video we're going to show you actually briefly trended on YouTube, and we're not sure why. And the only reason we found out is because we got these sorts of sterling reviews and comments. This is one of the more polite ones. Why is it trending? It was only because we got 4 or 5 of those comments that I figured out that it trended at all. All right, so let's show you some of those. So the first demo is just going for a vanilla shell, the most basic example. On the right-hand side, you've got the attacker's machine, and on the left-hand side, you've got the victim that you're going after. It's not connected to a network, just to show that we're not going to be using that network. And it's got the USB device plugged into it at the moment. Of course, just to have a little bit of fun, it's running McAfee, and we paid our money, so we get a green computer is secure. And if you remember, we were talking about the mouse jiggler to prevent the screensaver from activating. And so I'm just checking the screensaver settings, and you can see the screensaver's set for 1 minute. So if we pop up in the calendar, you can maybe close your eyes and wait for a minute. We'll see if the screensaver kicks on. No, okay, we won't do that. But we were quite chuffed to find out that you can't spot it, that you don't see the mouse jiggler moving. I thought that was cute. Anyway, so we hit a minute, I think there, yeah, and the screensaver doesn't activate. So at this point, we can now run our attack. So the idea is somebody's left for the day hoping their screensaver would activate, and it didn't. So we run our attack. I'm now talking, as I'm connected to the Wi-Fi that's connected to this USB device. It runs the things there. It's hiding the text, so now you just see the PowerShell window. If someone was looking at this, it would still be weird, a window popped up, but maybe not too outrageously weird. It's now moved the window off screen, but you can still see it in the taskbar. It's still got focus, it's still receiving keyboard input. Now it's finished, you can see it says sending some bytes. That's because it had opened up that binary pipe. It sent the second stage, and we end up getting our shell back over our private Wi-Fi network, running generic Windows commands, and because Dan Kaminsky did it once, there's a calc.exe. Yeah, so we managed to get remote access to that machine over our own Wi-Fi network. It was awkward. You guys made us wait.
Left us hanging. Okay, so we thought that was great, but we also wanted to be able to make use of existing attack frameworks. So what we did was we developed an alternative stage 1 payload that we could send over the USB HID connection that would act as a TCP proxy listening on localhost of the target's computer. And the idea there is that you've got these existing attack frameworks that expect to talk over a network. So we'll give them a network port that they can talk to, and then we'll translate that into the USB protocol that then gets sent over the Wi-Fi, and then it pops out the other end on the telnet port. So it listens on, for the moment, port 65535 on localhost. Localhost interface is obviously a good choice for an interface to listen on, because firewalls don't care, typically don't care, if you open up a listening socket on localhost. And the reason that is because you can't reach localhost from anywhere other than the local machine, which means that the software is already running on that machine, so it must be trusted. So the Windows firewall doesn't pop up at all, doesn't care if you're opening a new socket. And then that additional, that modified stage 1 includes some of the MSF, Metasploit frameworks, loader code that uses the PowerShell reflection to download a binary payload, DLL, and once that has finished downloading, it executes that. That connects back to port 65535, and then it all happens over the USB our pipe there. So
hit escape.
All right. So we've actually changed it up a little bit here. Rather than having it disappear, we've actually left the window visible. So you'll see the text change from gray to green, so indicating that it could have gone black on black. You'll see the window jump to show that it could have moved right off the screen. You'll see it minimized to demonstrate that it could have vanished entirely. But for debugging purposes and just to show you what's actually going on, it's handy to see the actual window itself. So once again, launching the attack. So on the right-hand side, we have the left-hand side, whatever. My right, yeah. On the right-hand side, we have the Metasploit framework running the multi-handler, standard multi-handler. It's set up to deliver a Meterpreter reverse shell. It's listening on port localhost 0000. Pro tip, don't ever tell Meterpreter or Metasploit to listen on an L host of 127001. It's a magic number. Shit breaks randomly. Works, it breaks. Works, it breaks. So that's why I was doing my dance in the middle of the night at Flamingo, because randomly it would work and randomly it would fail. Fortunately, thanks to Mubix, who spent some time with me after my demo, we managed to get it working in about 5 minutes' time, just with that pro tip. But thanks to Rapid7, they did buy us dinner as a sort of consolation for that. So we sped that up. It's a lot slower in real life. Our bandwidth is roughly 3K a second to be improved, and there is scope for it to be improved. And there you can see we've got our Meterpreter shell, sysinfo, who am I, sysinfo shell, who am I, and we're interacting with a fully fledged Meterpreter shell over a USB device that looks like a flash drive.
And what's particularly nice about that is it allows you to pull in generic TCP-based payloads. If you've got your favorite rat or Trojan that talks TCP, you can technically push it in there.
Could be Empire or whatever you prefer, quite capable of handling all of those.
And the joke for anyone who's followed Rogan in his career is Rogan built yet another proxy. Okay, so we then wanted to, what we said in the beginning was that the defenses for this are pretty poor. In reality, there are some defenses, but they're still pretty poor. So in Windows, you've got group policy objects that allow you to control what USB drivers get loaded in what way. So potentially what you could do is you could say, look, only allow the keyboard and mouse that we've got deployed in our organization and an iPhone or a BlackBerry. The problem with that is our device can impersonate any of those devices, and something like a BlackBerry or an iPhone gives us an innocuous device through which we've got a binary channel that we can send this. So you can change these attacks to deal with that. So the extreme version of that, which some sort of highly sensitive organizations do, is they lock down all driver changes. And what that practically means is if you unplug your keyboard and you plug it back in, it doesn't work. An IT administrator needs to come along and type a password. And I think anyone who works in a largish organization will know that that's probably untenable. And invariably, you're going to find the executives or the people who've managed to shout at enough people to get that policy turned off for them. So one of the suggestions that often comes up is that we have some kind of USB authorization framework. You have keys embedded in the devices, and there can be some cryptographic exchange, and then it's all good, only trusted devices will be loaded. So there's two problems with that. The first is that that's quite an expensive thing to do. And if you're looking at something like a keyboard, cheap commodity hardware, now this has to have a whole embedded key certification project that increases the cost quite a lot. The other is that, well, we can then just stick our device in one of those devices or extract the keys from them. So now you need to start having tamper-resistant keyboards and mice, which is maybe not realistic and maybe quite onerous for these sorts of things. So we don't actually have a decent solution for this, but what I think gets us towards a decent solution is if we can start instrumenting or at least exposing more of the instrumentation of your USB devices to software so that people can interrogate them. So for example, there's been talks about the USB hardware keyloggers, how you can detect those. And they're all things that you can't detect in software on the machine. But if we could, for example, expose voltage and power levels, maybe looking at the changes in power levels across machines on the network could be a useful indicator. I don't think that alone is going to do it, but the more of that you can instrument and expose at a software level, then the more smart people can come and develop detections on what those devices are doing. So it's not a solution, but it's maybe the start of how we can start finding one. All right, so this has all been released. It's open source. It's on our GitHub repository, Universal Serial Abuse. If you search on Twitter for US abuse, you don't find things that you're supposed to be looking for. The hardware is all open source. We're hoping to be able to make an easy to get version shortly. In the meantime, if you want to play with these attacks, the Cactus Micro is the device to go for. And if you want to contact us, those are our details.
One suggestion that came up recently actually was to build something like Little Snitch for USB devices, so that when you plug something in, it actually jumps up and says, this device that you've just plugged in has these capabilities. Is that what you're expecting? Yes, no. And one of the problems there is that you've got a little bit of a chicken and egg problem, that you've plugged in a keyboard. Please press yes on your keyboard in order to approve this keyboard. But this keyboard doesn't work yet. So there's some chicken and egg problems around that solution, but I think it could actually be reasonably usable. You plug in an additional keyboard into your laptop, or say yes on your laptop keyboard to approve this. The first keyboard will be accepted, and then subsequent ones will need approval. So there are some things that could be done.
Any questions?